Hello, everybody, and welcome to a new chapter with our electronic measurements and instrumentation module. Now it's maybe 2, 3 chapters to the end of this course or to the end of this module. Today we are going to transfer from maybe in the first 4 chapters we were mainly concerned about analog measurements, considering different instrumentation and different techniques, as well as environmental conditions, considering error as well as noise. Today, we are going to transfer from the analog domain to the digital domain. And as you believe, the best way to transfer from analog to domain to the digital domain is to study the ADCs, or the analog digital converters. ADCs will be considered in our module in a form of 2 successive chapters. In the first chapter, we are going to consider what I can call a system level consideration. So we are not going into the deep of the electronics. We are not going into the transistor level. We are just considering what we can say between quotation as a gate level consideration or a system level consideration, in order to understand the main concept of the ADC, as well as the different types of an ADC. In the next chapter, inshallah, we are going to focus on a specific type, which is mainly the SAR logic, the SAR based ADCs. And we are going to demonstrate some circuit level from this SAR logic, considering the sample and hold as well as a comparator. And finally, in the last lecture for this, or the last chapter for this module, we are going to study the reverse process, which is the DAC, or the digital to analog converters, again as a system level perspective. So let's now start with our today's lecture, considering ADCs, or analog to digital converters, again from a system point of view. Okay, let's start. So ADCs, or analog digital converters, are these electronic chips that use to convert analog signal into digital signal. Again, as usual, you can follow a more detailed description for our content using our main reference, Electronic Instrumentation and Measurement by Andreas Bell, going into chapter 5, or you can use our additional electronic resources where you can find it on the e-learning page. So maybe the question is why we should transfer analog signal into digital signal. And here comes into the comparison between the analog domain and the digital domain. I will not spend a lot in this comparison, because most of you already, due to the surrounding technology, can understand to what extent the digital environment is more consistent, let me say, and more powerful against the analog environment. But from the electronic perspective, what I can easily mention that what we call, or the term we introduced in the previous lecture with the analog noise analysis, the term noise immunity. So the noise immunity in the digital electronics is much, much, much higher than the noise immunity for the analog circuits. And conceptually, you can understand that in a very easy way when you go to the comparison between an analog continuous motion on the y-axis with respect to a discrete levels on the y-axis for a digital signal. So, for example, if I tell you that we have different 10 states from 0 to 9, and when I told you it's a discrete states, for example, 0, 1, 2, 3, 4, up to 9, and you receive a value of 7.7. So what you are going to say that, okay, this 7.7 is most likely 8. So it's 8, but due to some noise, it becomes 7.7. So the real estate is 8. But in principle, there is still a probability that it's a 7, and it has an over-induced noise of 0.7, so it jumps to 7.7. And there is another probability that this is a non-state with a noise effect that reduces the 9 into 7.7. But if I told you, yeah, okay, we have only two states, 0 and 5, and you receive a signal of 4. So now the probability that this 4 belongs to the 5 state is very, very high with respect to that this 4 belongs to the 0 state. This is simply the concept of when you minimize the states, you maximize the probability and you have a better noise immunity. So when you have a digital signals of 0s and 1s, the capability of detecting noise is much, much easier compared when you have a continuous analog signal that can have continuous variation on the y-axis or on the amplitude axis. Okay. Simply, when we describe the process of analog to digital converter, it's a very simple process that we need to convert an analog signal into a digital signal. But in order to understand the concept, or as I mentioned in the beginning of the lecture, the system level understanding of an ADC, we have first to understand what is analog and what is digital, so we can make a transformation from an analog domain to the digital domain. Simply, we can say that analog signal is, between quotation, the continuous signal. And what do we mean by the word continuous here? Simply, my dear students, is a continuity in both the y-axis variation, which is the amplitude variation, as well as the x-axis variation, which is the time variation. So the signal is continuous in both the amplitude and in the time. And on the other hand, when we consider a discrete signal, it's typically mean a discrete values in both time and amplitude. So in order to transfer from an analog domain into a digital domain, what you are simply seeking for is you need to transfer from a discrete and a continuous amplitude and time variation into a discrete amplitude and time variation. So herein, we need to make a double process of discretization. We need to discrete the y-axis, and we need to discrete the x-axis. And in this simple way, you can understand the two main processes of the ADCs using sampling, where we are discretizing the y-axis, quantization, where we are discretizing the time axis, and finally encoding, where we transfer these discrete system in both time and amplitude into code, into binary representation. And this is the general understanding or the general model or methodology for an ADC. Now, let's go into details. As I mentioned, sampling is discretization in the y-axis. So if you go to this signal here, maybe I can use the laser pointer for that. Yes. If you use here this continuous signal, as you can see, this is a continuous signal in the time axis and in the amplitude axis. What if we multiply this signal by a train of pulses? So in these gaps between pulses, here, 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 you are multiplying the signal by 0. So now the signal will not be defined in these gaps. And as the high state in the pulse is multiplied by the signal, simply the pulse will reshape its amplitude based on the signal amplitude, because simply you are multiplying anything by 1, you will get the anything. So this is simply how you are sampling the circuit. Of course, it's not that easy. And maybe in the next lecture, we are going to go to the electronics beyond this process. And I believe that in your communication modules as well, you go to the signal process, or you go to understand this process from a signal point of view as well, considering the Nyquist frequency and all this stuff related to the frequency domain analysis of these signals. But now let's just understanding from a conceptual perspective. It's simply like that we are taking a sample from the signal, and now our sampled version is here. As you can see, we are now discretizing the time domain. So only values here, only signals here are discrete or defined in a certain time variations here, around what we can call the multiples of TS, which is the sampling time. So at 0 TS, 2 TS, 3 TS, and so on. And otherwise, the signal is not defined. So now this signal is what we can call a semi-discretized signal. This signal is only discrete in the time domain, but still it's not discrete in the amplitude domain, or in the y-axis. Here, the values are continuous. This pulse can have any value, so we don't have a discrete values. So now we have to go to the quantization process. In the quantization process, we start to make a discrete levels. So this is the full scale signal. So let's say that if we are from 0 to 1, this is the first level, 1 to 2, 2 to 3, 3 to 4, and so on. And for each level, then this level of this quantized signal is then encoded into a representation. Here, as you can see, we have 8 states for the quantization. That's why we have 3 bits for the representation, which is 2 to the power 3. So we need 3 bits in order to represent the 8 states of our signal. So now this can be used in order to demonstrate the full process from having a continuous analog signal up to have a code which represented by 3 bits. And we can here define what we can call the resolution, which is the delta variation, the incremental variation in the voltage between each 2 successive levels. So simply, it's the full scale over to the power n, where n is the number of bits. So herein, for example, we have 3 bits, so we have 2 to the power 3. For example, if our full scale range is 8 voltage, then it's 8 over 8, then your resolution is 1 volt. That means that each 1 volt variation analog is converted to a code. And this is, by the way, is very, very, very important in understanding the ADCs. So let me continue with this example. If I consider that I have a full scale range of an 8 voltage, and if I consider that I'm representing this into 3 bits, so simply it's 8 over 2 to the power 3, which is 1. That means that the resolution of this ADC is 1. When I mentioned that the resolution of the ADC is 1, that means that if you have an analog voltage of 0.2 and an analog voltage of 0.7 and an analog voltage of 0.9, these 3 analog voltages will be converted to the same state of 3 zeros. And so on. If you have an analog voltage of 1.2 and if I have an analog voltage of 1.3, these 2 states will be converted to the 001 and so on. So the higher the resolution, the higher the error. The lower the resolution, the lower the error. And herein, we can say that, okay, let's go with a very, very high resolution. It's okay. You can do it, of course. I mean, with a very, very low resolution, I mean, low delta V, I mean. So, of course, you can do it, but that's required to increase the number of bits, which simply means increasing the complexity of your system. So you can go for 16-bit, 32-bit, whatever you want, but you are going to pay the cost of that as you are going to scale up the complexity of the system. From one hand, you make an added value because you decrease the error, because here this delta is representing an error. So whenever you decrease the error, this is something very important or very beneficial. But on the other hand, you have a very big disadvantage that you are also increasing the headache or the complexity of the system. Let's go to the transfer function of our ADCs. Here we have two main categories for the ADCs, what we can call the unipolar or what we can call the bipolar. And I believe that you can understand the concept from the name. So when we call it a unipolar, it seems that we are only considering a unidirection or a unipolarity of the input. So here we are varying from 0 to full scale. While we're considering a bipolar, we are varying from negative full scale to positive full scale. So here, this is a double dynamic range in terms of the inputs. So for the unipolar, for example, here we have a representation for a 3-bit unipolar. As you can see, one of the disadvantages of this 3-bit unipolar that your most significant state, which is 3 ones, will be correlated to or reflecting 7/8 times the full scale, not the full scale. So you are varying from 0 to 7/8 over the full scale, because simply when you start with 0 and you have an 8 states, so then the final state will be 7, not 8. So this is why we have a full scale of full scale -1, which is the least significant bit of our system, and this is maybe a drawback for that. But in the other case, when you have a bipolar representation, you can see that here we are varying from negative full scale up to full scale. The 0 middle is typically at the center, which is 110, which is typically the center, the fourth state. But again, you have to understand something very important, that if we are considering the same number of bits for representation, comparing unipolar with bipolar, you can see this. Here we use 8 state to represent from 0 to Fs, which means that each state represents Fs over 8. So we are scaling from 0, Fs over 8, 2 Fs over 8, 3 Fs over 8, 4 Fs over 8, 5 Fs over 8, 6 Fs over 8, and 7 Fs over 8, which is, of course, Fs here is the full scale range. So the delta variation here is Fs over 8. But if you use the same 8 states, the same 3-bit, in order to represent a double dynamic range from negative Fs to positive Fs, just here what will happen is as follows. So here, when you are varying from negative Fs to positive Fs, that means you are going to double the step. So herein the step between Fs and 3/6 Fs, negative Fs, of course, and negative 3/6 of Fs, which means that herein that variation is Fs over 4 instead of here the variation was Fs over 8 from one step to another, and that's mean that you are now doubling the resolution of the ADC, or in other words, you are increasing the quantization error. Maybe I think in the tutorial you are going to solve a problem considering the quantization error, and you will find that the quantization error is equals to delta square over 12. So, or maybe delta over 12, I'm sorry if I forgot. So in all cases, the quantization error is proportional to delta. Whenever you have a higher delta, you have a higher quantization error. That means that if you use the same number of bits, when you're comparing bipolar with unipolar, you definitely find that the unipolar has a lower quantization error with respect to the bipolar variation. Now let's go into a very quick overview into 5 different types of an ADCs: single slope, double slope, SAR, flash, and delta sigma. In the coming lecture, inshallah, we are going to make a very focused consideration for the SAR logic ADCs in some electronic perspective. But now let's go into a conceptual scanning for the 5 types of an ADC. Let's just start with the simplest one, which is the single slope ADC. A single slope ADC is simply a variation between the inputs and feedback signal coming from the counter here using a ramp signal. So you have a ramp signal here and you have an V input. typically a comparator is a two-state device. When the V plus is greater than the V minus, the output is high. When the V plus is smaller than the V minus, the output is low. So as far as your input is greater than the what we can call the reference lamp, it's not a reference because it's dynamic, but so as far as the input is greater than the ramp signal, then you are going to produce a high signal. So let me try to describe it in a better way. I will go to the annotation, and simply let's say that we have something like that. So this red signal is the input. So this is V input. And this green signal is a ramp signal. So as you can see, my dear student, as in this period, before the intersection, V input is greater than the ramp signal. So the plus is greater than the minus. So the comparator is going to produce a high signal. And as far as the clock is enabled, so we have an input clock, the counter will start to count. The counter will stop counting at this point when the V reference or the ramp signal intersect with the V input. In this state, V minus will be greater than V plus, and then this is 0, and then this is 0, and the counter will start to count. So you are counting the signal as much as your input is greater than the ramp signal. Otherwise, the counting will stop. So this is a very simple way where you can make an ADC variation. Sorry. This is more into electronics. As you can see, here is our controller and our counter. And this is a very simple ramp variation using a current source as a capacitor. So the capacitor is charging the current source, producing a ramp signal or a variation, the signal I just sketched. So this is simply like that. And you have here a variation. So the voltage in the capacitor is increasing in a ramp way as far as the capacitor is charging. So this is simply what happened in this case. So, okay, so we will result with this case. So the ramp signal here counts. Once this intersection happens, the signal coming from the comparator will drop to 0. And this duration or this number of counts represents the corresponding to the V input. For example, when the input is reduced, then this number of counts will be reduced and so on. We can represent this mathematically in this way. So we can say that, okay, we can say that V input, we know, of course, that I equals C dV by dt. So from this perspective, we can say that the V input is proportional to the current over the capacitance times the time, where T1 here is the time taken to reach the ramp signal to intersect with the input signal. This duration or the number of counts here is simply T1 over T clock. So this is the T1, which is the overall time taken by the V input, and T clock, of course, if we return back here, sorry, T clock is coming from here. So this is the number of counts coming from the clock. So for example, you can have a D of 100 counts, 10 counts, 12 counts, whatever. It depends on the duration of this T1. And here you can make a general expression for D as V input over I T clock over C. And this I T clock over T is very, very important in our case because this represents the minimum voltage needed to make a least significant peak variation. So in order to make a single count, you have to have a voltage that is corresponding to I T clock over C. This is the minimum possible variation that can be detected by the detector. So if your variation is less than 1 clock, you will not have a counted signal in the encoder, and your counter will not flip from 3 zeros into 001, for example, if it's a 3 bits ADC and so on. So this is simply how we can demonstrate the concept of the single slope ADC. But herein there is a very important point, that the variation here, or the consideration here, is depending on I and C, where I is the current source and C is the capacitance. So the main drawback on this design is that it can be affected with the tolerance of the components. If you are inserting a 200 picofarad capacitance, and this 200 picofarad capacitance is not 200 picofarad, it's 210 picofarad. This will affect the slope of this line, and this will affect the time, and will affect everything, and so on. Same applied on the current source you are inserting, and so on. So the main drawback, of course, the single slope is a very simple ADC conversion process, but the main drawback is related to its dependency on the electronic elements in the circuit. Herein we go to the other side, which is the double or the dual slope ADC. The dual slope ADC, as you can see, conceptually, it's not that big difference. Still, we have a comparator, we have a counter and so on. But we have two main differences. That instead of having this IC ramp signal, we have an integrator. I believe you already see this circuit before in your Electronics 1 module, where this circuit is mainly acting for converting the integration of the output. So here the output is 1 over R3 times the integration of the V input, if you remember. So here we have an integrator. And instead of having a ramp signal, we have a fixed reference voltage. And the controller here is acting to alternate the switch, either to connect the V input to the integrator, or to connect the VR to the integrator. In both cases, as you can understand, my dear students, of course, here this is a negative VR, and we can understand why it's a negative VR. So what will happen simply is something like that. When a positive voltage is connected here, that means that the current was going to flow in this direction. So the current is going to flow in this direction simply because this is 0, this is a virtual ground, and this is typically a negative voltage because the inverter, if you remember, my dear students, that the integrators are an inverting configuration. So if you have a positive input, you should expect a negative output. So this Vx should be expected in negative. So what the direction of the current here is something like that. From high voltage, positive voltage, to virtual ground, passing through the capacitor to a negative voltage. Okay, so this is the first scenario. When you connect here to the negative VR, still this point is ground, but this point will turn to be positive. So the current will flow in this direction. So when you are connecting the switch to the V input, that means you are charging the capacitor. When you are connecting the switch to the negative VR, you mean you are discharging the capacitor. In the end of the day, you will end up with something like that. This is the charging time, and this is the discharging flow. And this is the point we call it VM, which is the maximum voltage that can be charged to the capacitor. Herein, as you can see, the time T1 and the time T2 mainly depend on V1 and VR because R and C is constant. So if V1 and VR is the same, so for a chance, if the inserted voltage is typically equal to the reference voltage, what you are expected to see is that you're expected to see an equilateral triangle. So you can see that T1 will be equal to T2 and so on. Randomly, in any other case, one of these two values will be greater than the other based on the values of the V1 and VR. In general, you can say that VM from the left side point of view, VM equal V input over RC times T, which is simply VM, the total value, equal 1 over R3 times the V inputs times the time. And on the same case, if you go to the right-hand side of the triangle, this right angle triangle on the right, you can say that Vm also equals to Vr over RCT2. Because both are Vm, we can say, of course, RC are equal RC. So we can say that V input over R1 V input over R equal T2 over T1, or even equals to the number of counts N2 over number of counts N1. Now, VR is constant, and N2 is constant because you know already the number of counts for N2, and then you can know V1 considering N1, or you can know I'm sorry. VR is known, and N1 is constant, N1 is fixed. So you can say simply that the V input is proportional to N2. So what you do is simply here, my dear students, is that you make a ratio. So the main difference between the single slope and the double slope is in the single slope configuration, we rely on the INC in order to calculate the input. So the input is mainly based on INC. So if you have a tolerance problem with the INC, this will be reflected on the V inputs. But herein, it's a ratio. So if there is an error in the RNC, this error in RNC will be simply canceled, as you can see from this equation. So it does not depend on the electronic component or the tolerance of the electronic component of the circuit. However, it has another problem that you are going to take double the time, or not double actually, but 1 point something of the time you take for the single slope, because simply in the single slope, it's based on one variation. So you have just ramp signal. Once this ramp signal intersects with the constant input voltage, you calculate the number of counts, and this number of counts is proportional to the input. But when you go here, you have to go with charging and discharging process. You have to go with this process and then this process. So if we say that T1 here, if we say that the total time here is T1, we can say that the total time here is T1 plus T2. So here the conversion time or the inversion time is relatively higher. That's why we can say that that double slope ADCs are a bit slower than the single slope ADCs. So this is another way of an ADCs. One of the most famous ADCs is the successive approximation, or what we can call the SAR-based, which is a successive approximation register source. Again, as I mentioned more than one time, in this lecture, we are just considering concepts. Maybe in the next lecture, we are going more toward electronics. So the concept of the ADCs based on the SAR-based ADCs is very, very in a logic way. So it's based on what we can call a logic flow, or what we can call from the machine learning perspective that this is somehow of a regression tree. So simply, let's say that you are searching for a voltage that's vary between 0 and 8, for example. The first logic question is to ask is this voltage is greater than 4 or smaller than 4? Now you are distinguishing. Either you are in the first class, which is between 0 and 4, or in the second class between 4 and 8. So this is the first question. So you start with the most significant bit, 110, which is equivalent to 4. Then let's go to this direction here. If this voltage is if the answer here is yes and the answer here is no, so you are going to complete with the upper part of the tree, and then you are going to ask the second question: is this voltage is greater than 6 or smaller than 6? So this is the second question. So if it's smaller than 6, then it's a relay between 4 and 6. If it's greater than 6, then it's a relay between 6 and 8. So this is the second question. So we get a high here and a low here. Yes here and 0 and no here. So we are going to continue. So if it's greater than 6, then typically it's 1, 1, 1. So it's between 6 and 7. So it's the 1, 1, 1, 1, 1 state, and so on. So based on this logic flow, the SAR logic acts to determine which voltage is your input voltage. It's a continuous process. The number of iteration needed is simply the number of bits. So if you have a 3 bits variation, then you need to ask yourself 3 questions, as we did here, 1, 2, and 3. If it's 4 bits, it's become 4 iterations, and so on. So you can, using this logic flow, you can determine the voltage, your voltage. Still, it's a bit slower. Of course, when we compare it with the single slope ADC, which we can say that this is the simplest, fastest ADC with the source of error we already considered. But again, it's a very efficient way, and that's why this is one of the most famous ADCs used nowadays, which is the SAR logic-based ADCs. Another one, which is again very interesting one, which is the flash ADCs. And the flash ADCs are based on encoders. I believe that you already see something about encoders in your digital logic or digital electronics modules. So simply, an encoder is a converter that converts 8 bits variation into 3 bits. Of course, this is not the standard one. You can make it in more than different configuration, but in our case, this is an 8-3 encoder. So we are encoding 8 bits into 3 bits. And simply, we are here relying on 7 comparators. And the idea here is simply consistent with what you see here. So here, as you can see, we have a variation between 8 states. I'm sorry. We have a variation between 8 states. So if you are from 0 to 1/8, then you belongs to the first state. From 1/8 to 2/8, you belongs to the second state. From 2/8 to 3/8, you belong to the third state, and so on. Here we do this using these 7 comparators. So here we have 7/8 of Fs. Here we have 6/8, 5/8, 4/8, 3/8, 2/8, 1/8. So this is the negative terminal connected to the comparator on this. And here we have the inputs. So let's go from down to up. If now this is a V input, and now this is the V/8. Sorry, this is 1/8 of the Fs, or Fs/8, the full scale range over 8. Now, if your input is 0, which means that you are less. If the input is 1, which means that you are greater than 1/8 of the full scale, then, and all other inputs are 0, so which is this case. So these 7 inputs are 0, but only this one is high. So that means that you typically under the condition of 7 zeros, or say 6 zeros, 1 and 0. So here we have a 6 zeros and we have only 1 here. So this is the first case. Now let's go to the second case when this is 1. Once this is 1, the second comparator is 1, which means that your input is greater than 6/8 of the full scale. You don't need to see this one. Regardless, this one, okay, you are, because basically when you are greater than 6/8 of the full scale, obviously you are greater than 7/8 of the scale. That's why this is not needed split now. So once this gets to 1, once this signal gets to 1, that means you are jumping to the second state, which is 0, 0, 1. Now, if this comparator gives 1, which means that you are greater than 5/8 of the standard of the full scale value. So when this signal gets 1 here, you don't need to see these two lower comparators, and you are going to 0, 1, 0 state, and so on. Till you reach this case, when you pick one from here, when you pick one from this, that means that typically you are greater than 7/8 of the full scale, and that means that you are now in the highest state, which is 1, 1, 1, and so on. So this is a very simple configuration for the flash ADC, and we can use it in order to convert. Of course, the main issue with the ADC, with the flash ADC, is that your system is proportional to the number of bits. So if I told you, I will not do that, but if I told you, please sketch the schematic for a flash ADC, for a 4-bit flash ADC, that means you are going to have 15 comparators. And here you are going to have a 16:4 encoder, and so on. That's why the system is scaling up exponentially as you go with higher and higher number of bits. That's why, or maybe this is the main drawback with the flash ADC. Now let's go to the final ADC, which is Sigma Delta, or Delta Sigma ADC. This is again one of the famous ADCs relatively. The Delta Sigma ADCs actually is, I can say this is a hyper ADC between more than one technique. If you see this part of the ADC, you can find that this is a very typical, or it's an identical like what we did in the double slope or the dual slope configuration. So let me go back to the dual slope configuration. So this is again, yes. As you can see here, just compare this with this configuration. So it's typically the same configuration. So this is typically what we can call the Delta Sigma ADC. So this is the same. Here we have an enable. This enable just to add the number of counts. And here we have the control logic, and we have the counter and the latch. And this is a switch where we can vary between the input voltage and the reference voltage. So it's a hybridization between the concept of the dual slope and the single slope. Here we use the same add logic gate as in the single slope. Here we use the same approach as in the double slope. So we are combining both technologies in one under the name of the Delta Sigma ADCs. So this is again the final part out of the 5 ADCs we scanned today. In the coming lecture, we are going more into electronics. In the coming lecture, we are going to demonstrate more about what is inside these structures. So for example, in this lecture, for example, we demonstrate the comparator as a triangle. This comparator is a positive terminal, negative terminal, and an output. If V plus is greater than V minus, the output is high. If V plus is smaller than V minus, the output is low. This is simply what we did. But what is the electronics inside this comparator? We also study the sample and hold in a very simple way, that we are just multiplying a signal with a train of pulses. But again, what is the electronics behind this component, and so on. So in the next lecture, we are going more toward electronics in order to understand what is the electronic concepts beyond some of the basic electronic components used in ADC. Mainly, we are going to focus on the comparators and the sample and hold circuits, which is, by the way, also part of your design project. So maybe this will also affect your understanding for the project, and of course this will be reflected on the project discussion and assessment. And as I mentioned in the final lecture, we are going to consider the reverse process, which is the digital to analog converters. Thank you very much for your concentration, and see you later on in the next lecture.